Hello again. Today we start new topic, chapter 8 of Anderson book, which is called Normal Shockwave and Related Topics. Please do not forget to ask your questions in the comments. I will read them when possible, and you can also interrupt me with your questions during my speech, during my presentation. We have today 12 people participating, including me, so not so many with respect to total number of students. So I hope this recording will be useful for your colleagues and for you as well. Just a moment, I'm organizing today presentation on the other computer. Okay, normal shockwaves and related topics is an extremely important subject where we study not just the question of the simplest type of shock waves, but also we study different forms of energy equation, energy transformation, and processes in isentropic and not isentropic flow. Here we will see how simple to calculate supersonic flow in isentropic medium when the entropy and the total energy of the flow are conserved, and also we will see how to calculate simple cases of normal shock waves. Based on this discussion, future we will elaborate theory of oblique shock waves and expansion waves. So I hope chapter 8 will be clear for you and will serve as a base for our future discussions. Again, reminding, we have discussed last time what are the shock waves and two different types of shock waves. Here I will extend this information. We can say that there are different types of similar shock waves. They can be also separated in external shock waves, which are not limited by the size of the body, but they are caused by body and flow interaction, and internal shock waves, as you can see on the right of this picture. It's a shock wave which appears inside the supersonic nozzle. Also, this type of shock wave should be compatible with geometry and compatible with flow properties. Not always shock wave can appear. And as you remember from our previous discussion, each shape of shock wave is a consequence not just of the shape of the body or body geometry, but also consequence of flow properties before the shock wave. In this chapter, we speak about basic normal shock wave equations. To obtain these equations, we will need to talk about definition of the speed of sound, special forms of the energy equation, an extremely important case, an extremely important topic to understand not just this chapter, but also further ones. And when the flow is compressible, we can give a definitive answer based on flow model, not just as we had before, some definition of compressibility coefficient, and we said that flow is incompressible at Mach less than 0.3, but here we will prove numerically why is this number valid. After elaboration of the basic normal shock wave equations and related topics, we are talking about physical trends that cause interaction of body and flow, and practical application of normal shock waves in velocity measurement, especially in supersonic velocity measurement, where shock wave theory can be widely applied. So we have to start from the equation system. The same equation system which we saw last time on our previous class. It's a system that contains three main flow equations: continuity, momentum, and energy, and two additional algebraic equations, which are equation of state and internal energy definition. Set of these equations form for us complete closed system, which can be solved in some particular cases, specifically in case of shock waves and isentropic flows. The basic normal shock wave equations. This relation is this topic is starting from reviewing of these three flow equations: continuity equation, momentum, and energy. When we will try to solve these three equations, we will use definition of a simple control volume, which you can see on this picture. Control volume ABCD, where two edges are parallel to the flow, AD and this one, AD and BC, parallel to the flow, so flow will not change along these edges because all the flow properties are constant along these lines. The flow does not enter or exit. And the edges of our interest are edge AB and CD, where flow enters and exits normally to this control volume. Also, we can see that our control volume is split in two parts. Part one is where flow is entering before the shock wave, and volume two is where flow is exiting after the shock wave. Between subvolume 1 and 2, we have a shock wave. As you may see in future, this definition is very useful, not just for normal shock wave model, but also for another type of flow, like isentropic flow model. Equation 8.1 shows a continuity equation written in its stationary form, where we do not have time derivative. Going back to the equation system, we might see that complete continuity equation had this time derivative. Our assumption is that shock wave is stationary, does not move in space, and because of this, flow field of density does not change with time, same as momentum field does not change, and energy as well. So we will not have time derivatives on these three equations. It simplifies for us the equation system. So what is left from continuity equation is the surface integral of density velocity product, which is supposed to be equal to 0. Applying this integral in our control volume, we will see that edges AD and BC will not contribute to the mass exchange because velocity component is equal to 0 on these edges. And only edge AB and edge CD will contribute to this integral there is a sign convention that says that all quantities which enter control volume are negative and the quantities which exit control volume are positive. It's just a convention which does not depend on the final result. We could use also opposite sign convention, which would lead to the same result at the end. So how this integral can be calculated? For example, integral over edge AB. I will write here this integral of equation 8.1 will be a sum of two integrals HAB over density 1 velocity 1 ds1 plus integral of it's minus here before, plus integral from CD of density 2, velocity 2, and area 2 would be equal to 0. Here quite visible that area S1 and the area S2 are equal. Okay, they are same. So can use just ds instead of ds1 and ds2. And also we may see that density 1 is a constant along the edge and velocity 1 is constant along the edge, as well as density 2 is constant along edge CD and velocity 2 is constant along the edge CD. So we can rewrite this integral in a very, very simple way. It will be written as follows, will be density 1, velocity 1 multiplied by area with the sign minus plus density 2, velocity 2 multiplied by area equal to 0. Areas are same, so we can just cancel them from this equation. In a such way, we see the balance between density-velocity product at the inlet and outlet of our control volume. And we start to receive a very simple relation. Density 1, velocity 1 is equal to density 2, velocity 2, which says to us the quantity of mass which entered inside control volume is equal to the quantity of mass which exit outside from the control volume. This quite obvious, right? But now we prove this definition in a simple analytical way. Same thing we can review applied to another equations. Here equation 8.2 shows same as I wrote you on the previous slide, just the velocity was reduced to velocity component because in our case velocity vector is composed of velocity u and 0 because it's horizontal, it has just horizontal component of the flow, so it has just u component of the flow. This is why we have, instead of v, we have u, but in general v is also valid. V is also valid, especially when we will talk about two-dimensional case oblique shock wave, where we have two velocity components entering and exiting from the control volume. So now we can see the momentum equation written in the similar form. Momentum equation represented on equation 8.3. Here it can be also simplified. It's already in stationary form. It does not have body forces, just has pressure forces and has the momentum flux over the surface, the left side of the equation. And further, it can be simplified when we assume that our velocity consists only of one component. Instead of v velocity, we just use u component of the velocity. And since our control volume is rectangular, it corresponds to axis of coordinate system. Instead of integration over the complete area, we are integrating only in the direction of x. In direction of x, direction of v will not have any kind of integral. So that's these are simplifications. Now, if we open this integral same way as we wrote it for the continuity equation, we will see that quantities entering the control volume are having negative sign with minus u1, and quantities which exit the control volume are having positive sign. Just sign convention as we had before. Inside each of these product, we have same parameters as we had inside the original integral is density, right, the velocity, and area, and velocity. So this algebraic form exactly corresponds the integral form. Just the integral was written in a simple way because our control volume is very simple. I would like to see if everyone can see my screen, if it's visible for you, because looks like Beatrice does not have access to the screen. Please write me if you can see my screen. Okay, thank you. I see that screen is visible, so I can continue. Last week, I had one problem with sharing my screen in Teams as well, so now I'm starting to worry what could happen if my screen will not appear in Teams. But it looks like everything is good, so thank you for confirmation. The right side of the equation 4 can be represented in its algebraic form same way as the left side. We write integral of pressure over the area just as product of pressure and area. Here we can do it because pressure is constant along the edge and the area is same AB and equal to area CD. As we had before. So this area A is here, right, on the left and on the right side of our control volume. Now just rearranging equation in 8.5 and simplifying this equation by canceling, for example, area because it's present in all terms of equation 5, and rearranging parameters on the left side are inlet parameters on station 1, and on the right side are parameters on the exit. We are starting to obtain the simple form, an algebraic form of a momentum equation, one-dimensional case, because our velocity is just having one component. Even though the shock wave or any type of shock wave is at least b-dimensional, right? We have x and y coordinate. But since velocity is just going in one direction, we can reduce the problem from two-dimensional case to just one-dimensional case. This is possible only in a normal shock wave, but in oblique shock wave, you will see that we will use two equations in of momentum in two directions. Now you can already, I hope you start to feel what we are doing with our flow equations, and we may take the third equation of energy, written also in its stationary form, and we can process same way as we did previously. Okay, the left side is the flow of energy along the edge of control volume, and the right side is this energies related, flow of energy related to pressure forces. And absolutely the same way we are simplifying the energy equation, solving integral form of energy equation for simple rectangular control volume, and we start to obtain equation 8.8, where already cancelled areas and just have flow properties. Still, this equation we are simplifying because we can define from our classical definition enthalpy, which is internal energy plus PV product is pressure and specific volume product, or same as pressure divided by density. Plus internal energy gives us enthalpy. So we just introducing enthalpy inside energy equation can reduce the size of its of this equation, and we start to obtain our classical form of energy equation, which we saw last time, right? Is the balance of enthalpy on the left and on the right side of our control volume. And I also will put here probably that it's all equal to stagnation enthalpy, right? This enthalpy balance is constant for isentropic, and you will see also that for non-isentropic flow as well sometimes. Okay, summarizing all the analytical equations, we write all these 5 equations just in one place to show you the complete system of these equations. You may see that this system is simple set of algebraic equations corresponding to flow equations, and enthalpy and equation of state as auxiliary additional equations. What's the problem with this equation system? Why we still did not obtain the equation of normal shock wave? What are the parameters on the normal shock wave? Does this equation work? You may start to ask, because this equation system here is absolutely did not give us the answer. Okay, what would be the parameters after the shock wave? Why? How we can insert physics of shock wave inside this equation system? It's could be a very nice question. Would be a very nice question, especially when you see that we did not put any specific physical model or process that would describe transition from supersonic to subsonic region of this flow. What does it mean? It means that such an equation system which we just obtained can be valid not just for the case of normal shock wave. It can be valid for the case of also isentropic flow, or anything that happens inside a rectangular volume when we have just input and output and do not know what happens in the middle of this control volume. So such a model can serve for us as a template for other types of different types of flow, including shock wave flow inside this control volume. To elaborate an exact definitive model of the flow with shock wave, we needed to introduce another concept that would relate properties on the shock wave and thermodynamic changes or thermodynamic parameters of the flow. And this is exactly the thing we will do in the next section. Definition of speed of sound. This is what was lacking to calculate shock wave. Here is the schematic that allows to elaborate the model of speed of sound, or let's say the equation of speed of sound. Probably you already know from other disciplines that speed of sound can be calculated according to this equation, which is written on the left of this picture. But for our model, which we just have discovered, this equation cannot be applied directly because our equation system from previous slides does not have any kind of derivative. So we cannot put directly definition of speed of sound here. To obtain the definition of speed of sound in terms of thermodynamic properties, which could be used inside our equation system, we can use approach A, which is shown on figure 8.4, or approach B. These two approaches are equivalent. Approach A is showing us change of thermodynamic properties of gas when a wave is moving inside the gas. What is the wave? The wave is a small change of pressure, small pressure wave, a weak pressure wave that is always moving with the speed of sound. Sound wave. Okay, sound wave is a pressure wave. Probably you know this already from other courses. Pressure waves are quite common in our everyday life. You probably know that when we speak, we generate pressure waves, right? That change properties of the flow and alter pressure, temperature, and density. These pressure waves are quite weak, so we cannot feel them by skin, probably usually, right? But we can hear by our ear as a very sensitive instrument to detect pressure wave. This is how we communicate. Picture B is an equivalent to picture A. It just happens inside moving air, in the air which moves with the speed of sound. So we have an observer in picture A, stationary, and the sound wave is moving. And in picture B, we have same, but observer is moving together with the sound wave. So for an observer, sound wave is stationary and staying in the same position, and the flow is moving with the speed of sound, not just with the with the speed of sound. So the not the shock wave, the sound wave appears to be at the same place. We already have definition of sound wave, right, as an infinitely small pressure wave, and a shock wave. Shock wave is how to say? Yeah, shock wave is a set of sound waves that are accumulated, let's say accumulated sound waves, infinitely small or weak waves which because of some reason, can meet at the same place. This reason we will discuss soon. These sound waves meet at the same place and they form as a total a big and strong wave, which is called shock wave. For our discussion today, we will use approach B, and this is because our control volume from previous discussion is stationary control volume, which is not moving in space. So for us, it would be much easier to work in side stationary sound wave. So if I draw control volume around all this figure, here we have inlet station 1 and outlet station 2, station 1 and station 2. And our flow properties are changing. Pressure is changing. It becomes from P to P plus dP. Temperature also has some differential, as well as density and velocity. Velocity in this case is represented by letter A, is speed of sound, because we already agreed that flow is moving with speed of sound. Since temperature, pressure, and density change, speed of sound after the sound wave is also different. So it's A plus dA. So we can see here these 4 parameters. And we can use our equation system from previous slide to rewrite this equation system. For example, I will start here. Maybe I can, it would be nice if I write here. So we have, instead of U1, we have A. So density 1A, or, okay, let it be just density. Okay, station 1 will be just without any number, would be equal to density 2 is rho plus d rho, and velocity 2 would be A plus dA. Okay. The momentum equation will be written in the same logic. It will be pressure plus density speed of sound in square is equal, on station 2 we will have all plus the previous quantity plus differential. So P plus dP plus rho plus d rho, and multiplied by, forgot here, divide by 2, and here A plus dA in square divided by 2. Okay, like this. For the energy equation is same approach we can write. Okay, same equation. I hope it's no need to write this equation, but just to save some time. What we can find from this set of equations is, since this is a complete system, closed system, we can write what is speed of sound from this equation system. Here we have one assumption that product of 2 differentials is equal to 0. So we will neglect some products when we open bracket, for example, d rho multiplied by dA will be equal to 0. Okay, this. But when we just multiply, for example, speed of sound by d rho will be a product A d rho, like this. So we can find the speed of sound from this set of this equation system. Let me go back to this discussion. And in order to solve from differential equation, which you may see here on this slide, from this one, we will apply our isentropic relations that we had on our previous discussion. Isentropic relation between different thermodynamic parameters. These isentropic relations you may see here on the right, this equation here. When we join together, when we combine together the derivative of pressure by density, we start to have, instead of derivative inside our equation of speed of sound, just algebraic equation. Okay, this equation here. We also remember that according to the equation of state, pressure to density ratio is equal to temperature multiplied by gas constant. So this is equivalent. These are equivalent terms, right? Equation of state. P divided by rho is equal to RT. So this is the speed of sound definition, which we found from the equation system elaborated previously, and applying isentropic relations from our previous discussion. Now, not right now, but very soon we will go back to the model of normal shock wave. But before, Anderson proposes to talk about different forms of the energy equation. This topic is extremely important because it opens to us several possibilities in analysis of compressible flows. Okay, what are the forms of energy equations I consider important? We have initially equation 28 as an original energy equation from our previous discussion, equation 28, and its simplified form when we have just one-dimensional flow, equation 29, is the same when we have just a u component of velocity and we do not have v component of velocity. Okay, first thing that we must consider in equation 29 is that enthalpy can be written as a function of temperature. You remember that enthalpy is a product of temperature and specific heat, right? Can be written for any arbitrary point, is not dependent on type of flow, absolutely. And here we may obtain a very important equation, equation 30. This equation we will use in future several times to elaborate different concepts in compressible flow. Why this equation 30 is so much important? First of all, because it relates two points in space where we know parameters, for example, the inlet, and where we would like to know parameters. We would like to calculate parameters. How can we use this equation in a real case? In the following way, let's assume that we have a flow which is some arbitrary flow somewhere inside some duct or outside, internal or external, not important, where we have inlet point or input point where we know properties of temperature and we know properties of velocity, and we would like to know properties at any other arbitrary point. But usually we cannot put all necessary sensors on this point, can be because of several reasons. can be because some sensor will distort flow so much, so you will not be capable to detect properties of undisturbed flow. For example, when you create a shock wave because of you put too big sensor inside, so flow is changed definitely. You cannot take previous parameters. And sometimes some equipment can be just difficult to install in one or other position. For example, sensor of velocity usually is more complex than just sensor of temperature. Let's assume we can put sensor of temperature at some specific point where we would like to study our flow. So here at this point 2, I will put just thermocouple, so I can measure temperature too inside point 2. When I apply all my data inside the energy equation from equation 30, I automatically can obtain velocity at point 2 because it's the only unknown inside the equation. So this is already showing power of energy equation or energy of energy equation. When we can calculate some flow properties, just measuring some other flow properties and obtaining more complex parameters that could not be measured directly. Right. This is valid for compressible flows. All flows are compressible in real life, probably you already know, but some flows are less compressible. So equation 30 is better to apply in highly compressible flows when we can determine change of temperature because of change of velocity. Since energy is conserved inside closed system, we may see that energy on the left side of equation 30 is just redistributed in different way on the right side of this equation. So velocity can be easily obtained. Of course, equation 30 does not serve for all possible cases. For example, when we have case of energy consumption, like heat exchange, right, or generation of energy like chemical processes, then we cannot use equation 30 directly because this equation does not have necessary sources and sinks of energy. But in case when we do not have significant sources or sinks of energy in our system, equation 30 serves perfectly to obtain velocity or to obtain temperature. In some cases, we can measure velocity, but it's difficult to introduce thermal sensor inside some point. So temperature can be indirectly calculated, right, or indirectly measured in such case. Well, this is very powerful. I hope you understood. Then other transformations with the energy equation could be performed. For example, we can re-express product of CPT in other way, as CP is a function of gas constant and the diabatic constant. You can see it here. This relation here. So they are equivalent. How they are equivalent, we can easily show when we remember what is CP from previous lecture. We had CP. Okay, just looking to this equation here, and I will write is proportional to gas constant multiplied by gamma and divided by gamma minus 1. Okay, so equation 30 is having this CP, and we can re-express. What does it give to us? It gives to us from definition of speed of sound. This upper part of term is speed of sound in square. So we can say that we have some function of speed of sound at point 1 And on the right side, we will have also function of speed of sound at point 2. Equation 32 shows this equation, this relation between parameters of flow in two different points. So it's point 1 and speed of sound at point 1 and the point 2 speed of sound at point 2. Here we see such a form of energy equation which just contains velocity. It doesn't have other units, which is interesting for my opinion. So you can say what will be speed of sound directly from this equation if you know the left side, for example, of this equation from initial condition or inlet condition, or you measure it already, you can find relation on velocity and speed of sound at any other arbitrary points, a point in this system, or several points, because we can write just not for 1 or 2 points, we can write for 3, 4, 5 points, as many as we would like. You just have to follow the principles of the flow, right? The type of the flow should be conserved. Here also we cannot have sources and sinks of energy, just a transformation of one form energy to another form energy. For example, flow of air without combustion or without heat transfer. One specific case we may assume if we imagine point 2 as a stagnation point. I build a wall, so my flowing from somewhere impact on this wall, velocity is equal to 0 at point 2. When velocity is equal to 0, it means that my final part of equation 32 will not exist anymore, and all my thermodynamic flow properties become stagnation properties. T0, P0, rho 0 is maximum values. And because of this, our speed of sound starts to be stagnation speed of sound. How to calculate stagnation speed of sound is using absolutely same formula as normal speed of sound. A0 would be equal to square root of gamma R. Oh, sorry, my R is not so good. RT0. So formula is the same as for ordinary speed of sound, just instead the static temperature, you need to use total temperature of the flow, or stagnation temperature of the flow, temperature at which you are calculating this speed of sound. So you must know quite well that if you want to calculate the speed of sound in any specific point inside your flow, you need to use temperature at the same point. You cannot use temperature in other arbitrary point you want. You need to have absolutely same point for calculation. And then you obtain speed of sound. This is valid for any particular point in the flow, and also valid for stagnation properties when flow is stopped until 0. So stagnation speed of sound. Equation 33 shows to us this relation, this form of energy equation. And what is interesting, that stagnation speed of sound, according to this equation, since we can choose any relations, right? And everywhere energy will be same. So it means that since stagnation speed of sound is the only parameter inside equation 33, and we have constant energy in the system, it means that A0 is also constant for a closed system. So A0 as stagnation speed of sound characterizes also the complete system, or energy of the complete system. If we will see another specific point like shown in equation 35, this is the following case. Okay, we have flow point 1, from where flow starts, and then some specific point we will mark it with asterisk. What happens at this specific point? We have flow velocity equal to speed of sound. At this case, we have same, we can write in terms of Mach number, since Mach number is velocity divided by speed of sound, so it means that it will be equal to 1. So if we have such a point in space that would have Mach 1 of flow, this happens in many different cases. For example, inside the nozzle, in the throat, in the smallest section, right, of the nozzle, we have such flow conditions. It means that such flow conditions can be always calculated from energy equation, from one of the forms of energy equation. How it was obtained? We just use our equation 32. I will remove some notes here, and instead of velocity 2, I just changed to A2. So we have speed of sound in both parts of right side of equation 32. And here we just combine, because A2 and A2 are same A2, right? We just combine, and inside equation 35, we start to receive this definition here. This condition of the flow when Mach number is equal to 1 will be used very soon, and will be used in many different applications. It's used in theoretical gas dynamics, and it's called characteristic point. Characteristic point. Okay, you can find in literature when you see characteristic point, it means that the point at which Mach number is equal to 1. Okay, characteristic point at which Mach number is equal to 1. And if you read in some book, for example, characteristic speed of sound, you will know that characteristic speed of sound is the speed of sound which happens at that point. It means that speed of sound at point when velocity is equal to speed of sound, or point at which Mach number is equal 1. So same, absolutely. Characteristic point. This characteristic point is not just characterized by Mach 1, it's also characterized by specific value of speed of sound. It's characterized by specific value of temperature, density, and pressure. This will be probably just one of the next slides or next slide. Formula 36 proves that when we apply our energy equation, original energy equation, to the concept of characteristic speed of sound, we may see that since characteristic speed of sound is the only parameter we have on the right side of equation 36, this value is constant for our system, same as we had stagnation speed of sound constant for any system. Characteristic speed of sound is also constant for closed system, for a closed system. Relation between stagnation speed of sound and characteristic speed of sound you can see on equation 37. Clearly shows that just proportional to function of adiabatic coefficient, right? Adiabatic coefficient for us is constant, so A0 is proportional to A asterisk, have a linear relation, not dependent on value of pressure, temperature, density, or velocity. Just speed of sound at the point where flow stops. Okay, for example, some point at flow stops. Will be related, according to formula 37, to speed of sound where Mach number is equal 1. And this is another nice tool to evaluate our flow, because look, for example, I have flow at which my flow stops definitively. I have a wall. And on this wall, I put my temperature sensor and I measure my stagnation temperature on this wall. What does it mean for us? When I know stagnation temperature, according to speed of sound function, I calculate speed of sound, A0, and since I know relation 37 and I know A0, I can calculate my characteristic speed of sound. After I do this, okay, I will make here this algorithm continue A asterisk, okay. Oh, sorry. Let's make it on upper script. And when I have this, I can calculate my characteristic temperature at the point where Mach number will be equal. So inside the throat, for example, of the nozzle, inside in the middle of the nozzle. So if we have the nozzle, throat, Mach 1 here, right? So we can know what is the temperature in the throat. Just if we measure some temperature here when flow was completely stopped, we did not measure anything inside the throat, but using one of the forms of energy equation, we can predict what is the temperature in the throat. We did not measure even velocity, right? We do not need velocity. We can know temperature in some specific point just using equation 37. That's it. Quite useful. Very important thing. Next form is helping us to elaborate isentropic algebraic isentropic relations in the flow. Equation 38 is just repeating one of the previous equations. Let's see, Cp multiplied by T we already had before. So this one, this equation 30, is equation 30. We just assume that we have isentropic, not isentropic, sorry, we have stagnation point at point 2, so we will not have any kind of velocity, and we just will have temperature. Since velocity is equal to 0, temperature 2 becomes temperature 0, 2. Okay, so becomes stagnation temperature. And this is equation 38. Is absolutely same, another form of energy equation. Why this form of energy equation is important for us? Because we can use this form for elaboration of other change of parameters of as in, we call them isentropic relations when the entropy remains constant. How we do it? We use definition of thermodynamic relations, which you already studied in previous subjects, and we saw on today and on previous lecture. And in this equation 41, we have a relation between two arbitrary points inside the isentropic flow. These two arbitrary points are point of stagnation when velocity is stopped, and any other point where velocity is not stopped, point of our interest is, it says that ratio of pressures is proportional to ratios of densities in the power of gamma and proportional to ratio of temperatures in power of gamma divided by gamma minus 1. So we just need the ratio of temperatures, and we can work with other thermodynamic properties. How to obtain ratio of temperatures, for example? Using equation 38, we rewrite this equation in a such way that it becomes a function of Mach number. How it's done? Let's see. Let's make a small a small exercise, right? For example, I will divide all by CP, right? I will divide all by CP, this equation 38, and I will put on the left temperature ratio. Okay, so let's divide all by CP, divide all by T then, right? Let's try at least. I hope we can make it. So when I divide by CP, I will not receive CP here and here. I will just have CP right here in denominator. And then I will divide by temperature left and right side. So I will have here just one, okay? And I will have temperature here, and I will have temperature here. I hope for now it's correct. So we start to receive U in square divided by CPT multiplied by 2 equal to T0 and plus 1. 1 plus 1 remains from the first part of the equation. T0 divided by T. Okay, and now we remember relation. Now something. Oh, okay. And now we have to remember relation between CP and speed of sound. You remember that they are related. And Mach, sorry. Let's go upper, where we wrote this relation here. CP is R gamma minus 1. So when we will put this inside our equation, gamma minus 1, gamma will be here. Okay, R, let's write here. So I have 1 plus U in square gamma. Here will be gamma minus 1 R. This is from definition of CP. Then we multiply by T and multiply by 2. This is what we already had. Will be equal to T0 divided by T. Okay, now it's clear because this part right here is speed of sound in square. So I have 1 plus U in square by A in square. So it's Mach in square as we have in equation 40. And gamma minus 1 divided by 2 equal to T0 divided by T. So I hope it was clear how I obtain equation 40. If there is some problem to understand how equation 40 was obtained, please let me know in comment. I will show you. I will try to explain better. Anderson also is doing this process in the book, so you can, or if it's not clear, ask right now or read the book where is explained in the same way as I did here. We, instead of this product of velocity, start to receive Mach number in square is the same, right? So ratio of temperature is obtained as a function of Mach number. Why is interesting for us? Because we have relation on temperature between stagnation point and any arbitrary point as a function just of dimensionless criteria of the flow, Mach number. When we have, for example, measured temperature in 2 different points, one in a stagnation point, another temperature in any arbitrary point, we can immediately say which is Mach number at this point. where we measured our temperature. Or vice versa, if we know Mach number at some specific point, we already can say which value of temperature ratios we would have in our system at any arbitrary point. For example, I have flow at one point stopped where I measure 1000 Kelvin. Let's have this example. Here I measure 1000 Kelvin, and I have this flow, okay, is passing somehow. This almost stopped here, but okay, since it's isentropic, some part of flow goes around, so it's not stopped in all the volume. It stopped just in one point. And in other point, I know that I will have, like in the nozzle, for example, Mach 2. So what does it give to me? I put my Mach 2 here, and I put temperature I measured in stagnation point here, and I will know my temperature here at Mach 2. So temperature where I will have Mach 2, I will be capable to calculate analytically without introducing any kind of sensor, just with analytical method. So look, I measure one temperature in some specific point, and I calculate completely in different point what I want. And not just temperature, also other thermodynamic properties in the same way. When we use equation 41 and we transform from temperature ratio, for example, to pressure ratio. Look, this, okay, we combine equation 40 and 41, and we obtain equation 42 or 43, where we have relation between Mach number at any arbitrary point and pressure and density at the same point. Of course, we need a reference. We always need a reference. So our reference point is the stagnation point. But as you will see in future calculation, reference point cannot be just stagnation point. It can be any point where you know flow properties. We can always make transformation from stagnation point to other arbitrary point, and we can calculate all set of thermodynamic properties according to these functions. Very powerful tool. Probably these equations are one of the most important in isentropic flow. Relate velocity in dimensionless and thermodynamic properties of the flow. Okay, people, how we can use this in practical life? It's very difficult to every time to calculate by hand these equations. I mean, look 42, for example, or 43. Is not simple. You cannot calculate by hand because gamma divided by gamma minus 1 is how much? Is 1.4 divided by 0.4 is not an integer number, and you cannot make inside head this. Probably not all can provide this calculation. So need some tool, right calculator or computer to calculate. But what we do in the class, every time we'll calculate using these formulas with power. It looks very heavy, right? So there is a practical tool that allows us to provide these calculations in class or for any kind of experiment or test, just simple, very in a simple way. So equation 42 and 43 are complicated. Equation 40 is simpler, but still you need to provide several computations. You need to divide, to multiply, and probably summarize, right? This is not also 1 moment, 1 second calculation. So our tool to calculate this equation is appendix. Appendix A provides to us relation on isentropic flow properties. This appendix is inside the Anderson book. Okay, it's the appendix of Anderson book. There are several appendixes. Appendix A is devoted to isentropic flow relations. How to use this appendix? We have tabulated all these functions we discussed before, plus area ratio, which we will touch just talking about flow in the nozzle, not in this section, but in the chapter 10. So for now, forget this area relation. We just will focus on Mach, pressure ratio, density ratio, and temperature ratio. These functions are tabulated. So we have variation of Mach number starting from 002, 200s, until Mach 50 in supersonic, right? Or hypersonic already. Properties quite a big range of Mach numbers, and as a function of this Mach number, we have pressure ratio, density ratio, and temperature ratio, starting from 1, right, and increasing. I think increasing, probably. Yeah, increasing until very high number. You can find at the very end huge values. For example, for Mach 2.5, we have pressure increased 170 times. We have density increased 7.6 times, and we have temperature increased 2.25 times. What are these values? These values are all written in engineering units. Just to be sure that all of you understand what are engineering units, I will explain one time. What does it mean? This 0.2 minus 0.1, what does it mean? Is a coefficient. 0.2 is a value. Is okay, let's have A. This is value A, and second is value B. So how to interpret this value is, sorry, just a moment, I have one problem here. Okay, looks like it's recovered. Is A multiplied by 10 powered by B. Okay, so it means that 0.2 multiplied by 10 minus 1. So this point is 0.2, 10 minus 1. It means that it's 0.02. Okay, in the same way, all other numbers, like for example, this value here, let's see, 0.1003, 10 powered by 1. So it's basically 1003. Okay. Let's see another number, another page, just to be sure that you understand the idea, how to convert to usual floating point number. You already saw these engineering units in Fluent, for example, right? When we, by default, simulate any type of flow, we receive legend in engineering units. Just to be sure that you understood, I will use this number here. So it's this value has to be multiplied by 10. So it's 1371. I hope it's clear. Please, if someone did not understand how to convert engineering units from Appendix A to normal values, numbers with floating point, please let me know if it's not clear how to do it. If it's clear, please stay silent. So this is the Appendix A. It has low values of Mach number. It has incompressible values of Mach number. Let's say, for example, almost from 0.2, we can see here 0.3. I skip one page or 2 pages. Is not the next page, which this one is not next page. It's after some pages. Just wanted to show you transition on Mach 1. Okay, because we have Mach 1 here in the middle here. This is Mach 1 characteristic point, right? Characteristic point, which you already know what does it mean. And the next page, I also skip some information, I think 1.2 and here 162. I skipped just to show you high values of Mach number. For example, here we have Mach 2, Mach 2.5 right here at the end. Let's choose some point, some arbitrary point. So, for example, Mach 2. I know that for Mach 2, this would be my pressure ratio. So when I have Mach 2, my P0 divided by P would be equal to 7.824. Okay, yeah, looks like. And let's see temperature also. Density, also same logic, but I would like to write just temperature. Temperature 0 by temperature would be equal this value, 1.8 equal 1.8. So how we understand this data? We understand them in the following way. When flow will reach Mach 2, pressure in any specific point, not in this specific point with Mach 2, will be 7.8 times smaller than stagnation pressure, which is our reference. Or vice versa. If we have Mach 2 and we measure at this point our pressure P, our stagnation pressure will be 7.8 times higher than this pressure P. Same for temperature. Okay, let's have another picture, something like this. A nozzle. I like to draw a nozzle. It represents very nicely isentropic flow. Stagnation point somewhere here, right? And Mach 2, somewhere here in supersonic section. We measure temperature anywhere we want, right? For example, I measure it in stagnation point. So if I measure temperature in stagnation point, then according to my function, I will know that pressure at point of Mach 2 will be 1.8 times smaller than stagnation temperature. Vice versa, if I'm not measuring inside stagnation point, for example, stagnation point is too hot, I prefer to measure right here this temperature. I know that my stagnation temperature will be 1.8 times higher than I measured in Mach 2 section. I just need to be sure that I measured exactly at Mach 2. So this is another big story, how to validate where point you measure. Usually we measure in different points. It's not exactly Mach 2. Then we need to estimate which Mach were in this section, and then using table according to Mach estimated, I can see which are flow properties according to isentropic relations. Isentropic relations are not valid for all possible cases. They are limited to isentropic flow. So please be careful, take in mind that if you are using some calculations for non-isentropic relation, you need to be to estimate first how big are the errors, how big could be the mistake using these relations, and just accept or choose another method for calculation of flow properties. There are other methods, not just this one. We will see them. So this is the next one, appendix 1, allowing us to not calculate using these isentropic relations, but to just choose values from table quite fast, rapidly, in direction from Mach to thermodynamic properties, and vice versa from thermodynamic properties to Mach number. So it can go in both ways. Okay, that's it. Probably one of the last things I would like to show you today are simplified isentropic relations when I can go back to formulas. Let's assume in these formulas I have characteristic point, I have Mach equal 1. So instead of Mach number and square, I have 1, and here and here. This is my characteristic point, throat of the nozzle, or any other conditions where Mach equal 1. In this case, right part of equation 40, 42, and 43 becomes constant. It just dependent on gamma, adiabatic constant. So is a value which will never change. It means that right part of this equation, pressure, density, and temperature ratio, will also stay constant and will not change. Just according to this formula, right? And these simplified relations you can see here on this screen, 44, 45, 46 represent relation between characteristic point and stagnation point for all thermodynamic properties, given as just values, right? Depend on which gas we are using. For air, is simple. Gamma is 1.4. Right? Gamma is 1.4. So you can see that ratio of temperature, pressure, and density is fixed between stagnation, any stagnation point, and characteristic point inside our flow. Sorry, my voice is already down, so I probably will have to finish soon. Just closing this question, I want to tell you that there is always transition, a formula which allows to calculate flow in different terms of Mach number and characteristic Mach number, formula 47. Well, characteristic Mach number is, m asterisk is velocity divided by characteristic speed of sound, which is constant for our system. We already saw it, right? So there is a relation between ordinary Mach number and characteristic Mach number. This relation is obtained from one of the forms of energy equation, one of the previous equations. Anderson shows how to do it in a very few steps. I think no need to stop on this question. And also reverse transformation is possible when we have ordinary Mach number m equal to v divided by a. And we would like to transfer to characteristic Mach number m asterisk. It can be done using this relation. Is the solution of equation 47. Analytical solution of equation 47. And as the final point, Anderson gives a relation between characteristic Mach number and real Mach number. It says that when characteristic Mach number m asterisk is equal to 1, m would be also 1. When characteristic Mach number is less than 1, m is subsonic. For characteristic Mach number more than 1, m is supersonic. And when real Mach number goes to infinity, according to analysis of function 48, m characteristic will reach its limit, gamma plus 1 divided by gamma minus 1 under square root. Okay, I hope this information will stay in your head until Thursday, because on Thursday we're supposed to use these definitions of characteristic Mach number and finally elaborate equations for normal shock waves. Okay. Please let me know if you have questions. I'm ready to answer some questions. If you do not have questions, I think we could finish for today, and we can continue next time. Please write in chat. Oh, nice. Jan already left. No questions. Someone has no time to wait. Tudo bem. Okay, people. Thank you for participation. Yes, all classes are recorded, and you have access to these classes on the Microsoft platform. I would like to put also these classes to YouTube platform in case Microsoft will have problems or will disappear in some time. I do not want to lose these classes because I think we need such information, additional information for your studies. Thank you very much, people, and have a nice week. We meet in 2 days. See you then. Bye.